down to the tip, at which point the small orifice bore starts. That defines your nozzle diameter. There is some slight variation, with the cheapest ones just drilled with a standard 118 degrees drill tip. E3D tried to improve on that many years ago with a step bore, probably to improve internal flow, but now uses, as many other higher quality manufacturers, a special drill bit with a pointier tip for better flow characteristics. Ultimaker still uses a special step geometry in their AA print cores, maybe for less oozing during retracts. So these are all just slight variations of a simple design. This right here is Bondtech's new CHT nozzle that features a special core that splits up your filament into 3 separate channels. CHT means core heating technology, which means that the material is not only melted from the outside in, but also from the inside out, promising higher melt rate. Get an idea how they probably manufacture the unique geometry. Instead of one straight bore, they drill 3 times at an angle, which all terminate at the same point. I assume they first pilot drill with a bigger bit to create the sharp edge, and then use a 0.2mm drill bit for the material channels. Really clever design, and I bet tricky to manufacture at this size if you're not careful. The thing that surprises me at first, but gets clearer if you take a look at my reverse engineered CAD model, is that the core, for which the C in CHT stands, is way smaller than one might expect and looks more like a blade that splits the material rather than significantly contributing to the heating of the material. A screw, which is smaller with the claw relief shape compared to a circle. Having the heating core in at least part of the nozzle makes that even better, and due to the sharp edges, it also shouldn't constrain flow too much. And then there is the overall conical shape of some heat, so it takes a while until the solder properly flows. I made sure to use lead-free solder and shows a superb performance until 40 cubic millimeters a second and only then drops off. Let's now get to the DIY high flow of 10, 15 and even 20 cubic millimeters a second. So at least outperformed a regular nozzle. Even at 25 cubic millimeters a second, there isn't any real performance drop visible. After that, we see the 120 degrees rotated to each other. Constrained flow, I increased the internal diameter of the nozzle from 2 to 2.4 millimeters on the length where the wires will be. Then I used my ancient vernier height gauge to mark the height of the bores and used the world's tiniest center punch to create indentations at these locations. Using this approach made drilling the 1mm crossbores so easy, and they all ended up perfectly centered, which made me at least a bit proud. Then I cut short pieces of 0.8mm copper wire and stuck them into the holes. I preheated the end result. To get a working nozzle again, I snipped off the ends of the wire and recut the threads with an M6 die. Not the prettiest, but let's see if this Übervolcano works. Performed basically the same like a longer volcano nozzle, and the Übervolcano beat everything by a wide margin. The